Okay. So we have much to get through today. So let's talk a couple of things about, on the assignment from yesterday, let's talk about, first off, question number 5.
Yes, please.
Okay?
Oh, a doozy.
It was a doozy.
She was a doozy.
Okay. So,
Question number 5? Yes.
yes. So, at the beginning, you're pulling this block at a constant velocity of 5 meters per second. Now, did I have to actually give you the value of the velocity? No. The only thing you know, the only thing you have to know is that it's at a constant velocity. That's it. Okay? It could be negative 5 meters per second. It could be a positive 10 meters per second. It doesn't make any difference. As soon as you see constant velocity, all of the forces together have to add up to 0. So, you're going to have 4 of them. Now, don't get confused with this FG. FG is the same as weight. Weight and gravitational pull mean the exact same thing. Okay? Don't flip out. They're both in newtons. I'm either asking you to find one of 2 things. Either mass, which is going to be in kilograms, or a force created by gravity, which is going to be in newtons. Okay? That's it. Boom. Those are your only 2 options. So if it's not mass, I'm asking you to find a force. Okay. So you got mass of the block. You can go, oh, mg. You're going to know this number. You know, mu equals force friction over force normal. You're going to find the force normal because you know what Fg is. Don't worry about making any of this negative for now. Just get your force friction, then decide if you need to make that positive or negative. So if you look on this question, here's your sheet. So there's an important part on question number 5a. It says the coefficient of friction, how much horizontal force must be applied? I'm not asking for the frictional force. I'm asking how much force has to be applied. So because it's already moving with a positive velocity, my applied force in this situation is going to be positive. Okay? Because it's moving with a positive velocity. Now, if I had said how much frictional force has to be overcome, you'd have the exact same answer, but it's going to be a negative number. Okay? So pay attention to what you're asked to find. If it's positive velocity and how much force does it take to push it, that's a positive answer. If it's a positive velocity and you're asked to find the frictional force, that's going to be a negative value. Okay, so there's a big difference between the 2. Now, on B, I want to know if you stop the force that is pushing the box and watch what will happen. This goes back to this whole idea of what we talked yesterday, this Jedi Stoffelwalk. Stop the force and watch what happens. Okay? So if you stop pushing the box, what's the box going to do? It's going to stop. It's going to accelerate. So if you ever stop applying a force and that the motion of the object is something different, that means you were causing a particular type of motion. So I'm pushing this marker and I stop applying the force, it immediately begins to slow down. That means that friction had to be there. If I stop the force and it maintains a constant velocity, like the hockey disc out in the hallway, that means there is no frictional force. And it's just going to move in a straight line. So here's what's vital on part C, when you find this acceleration. So here's what you want to look at on 5C. So you were initially having some force applied, and that force applied should be something around your current age. Okay? Something around your current age. That should be your applied force. So that's around 18. And the only reason that exists is because there's a frictional force of negative 18 newtons. So here's the deal. I wrote this with the idea that you understand the difference between constant velocity and accelerated motion. As soon as I stop pushing it, I lose my applied force. But what is still there? Friction. This now becomes an unbalanced force. When you have an unbalanced force, you get an acceleration. So My normal force isn't going to make it accelerate because that's just balancing out my gravitational pull. So with this one, I lose my applied force. The only thing I have is that frictional force. Divide that by the mass, there's your acceleration. So your answer to 5C should be a kind of decent GPA. Okay? Not stellar, but not bad. Okay? And it should be a negative number because you're slowing down with positive velocity. If you have a positive acceleration, that means that this thing is speeding up. Okay? So it's vital that you pay attention to the little things in terms of sign. So when you get to 5D, I want the total distance that this thing is going to travel. You also need to draw a velocity time graph indicating this. So basically, the short version of this is your velocity time graph is going to look something like this. Anytime you have a horizontal line on your velocity time graph, what's your acceleration? 0. Okay? There is no acceleration, which means your net force, which is the sum of all of the forces, is going to equal what? 0. So as soon as you change the slope of that velocity time graph, that means your net force is now something other than 0. Because now I'm going to start slowing down. Well, as soon as I stop pushing it, what's the only force that's going to make it slow down? Friction.
Sorry. Okay, I said roast me.
I honestly thought that was Shart's answering.
Okay. It's got to be the C. It just makes you say dumb things.
Then don't sit there.
It's also a better angle. So.
Okay.
It's a toss-up.
It's okay. So anyway, here you need two things. You need the net force, which is just going to be your frictional force, and then you also need that acceleration. So you need to find this total area. That total area, for which is your displacement, should be somewhere in the 30 range. Wait, are we happy about that? Yeah. Okay. Because at a minimum, you're going 30 meters because you're traveling at 5 meters per second for 6 seconds. So at a minimum, you're at 30 plus whatever distance it travels after it slows down. Okay? Good with that one. Okay. Now, let's talk about what's going to happen on 8 and 9. Actually, let's talk about 6 through 9. 6, 7, and 8, all of your exponents on 6, 7, and 8 should be something times 10 to the third. Okay? All of those should be something times 10 to the third. Your answer to number 9 should be something times 10 to the fifth. Yes?
Does it have to be in that form?
No. I'm just.
Okay.
No, it doesn't have to be, but I'm just saying if you did, that's where it's going to be. Okay? Now, some of your answers on this assignment should be negative. Okay? If you don't have any negative answers, just don't go through and randomly chuck negative signs on. Bad. Figure out why they should be negative. Now, let's talk about number 10. Here was my thought process on number 10, why I wrote this like I did. And we'll talk more about this once we get into the actual gravitational fields. But everybody has this idea that, oh, gravity is the same for everything. Love of God, it is not. Look, if I've got Hank the bowling ball and a golf ball, right, and I hold them up, I guarantee you gravity is acting much more strongly on Hank than it is on the golf ball. Okay? No comparison whatsoever. None. Now, here's the whole point. Hank has more stuff in him. Okay? Hank has more inertia. So therefore, when I drop them, I get the same acceleration, not because Hank weighs more. I get the same acceleration because there's more force acting on Hank, but it takes more force to get Hank to the same acceleration as it does the golf ball. Because if I apply the same force to both of them, if you go, oh, gravity is the same for everything. No, it's not. If gravity was the same amount of force for Hank and the golf ball, if gravity was the same force, I don't care what the force is, it's just some amount of force. If it was the same for everything, the golf ball would accelerate a lot quicker because of the fact that it has less mass and it would accelerate a lot faster. So the whole point on question number 10 is that I'm forcing you to look at this idea that gravity is not the same value of force for everything. Do I end up with the same acceleration? Yes. But it isn't because it's the same amount of force. Okay? That's the big difference. So that's the whole crux of what's happening on problem number 10. Okay? All right. Any other questions on that assignment? Going once. Going twice. So get that handed in. All right, so here's the next big thing.
He's my buddy.
I'm happy.
I'm not doing anything. You can't get
I realize I'm not. I'm just scowling at
What is the
sides
helicopter?
Just chill out.
Helicopter parent.
Okay? Yeah.
All
right.
Helicopter.
So, okay. So, this next big concept, and we're actually going to spend about a week going over this. It's this whole idea of net forces. What?
Can I get a second copy of these notes for Eric? I'm going to see him after school today. So I
Hand
can-
Oh, well, here, you don't have it in this reference. Okay.
Okay. So, if I'd make a list of saying, okay, what are some of the most important things that you have to thoroughly understand coming out of this class? Net forces would rank up there, if not number one, probably definitely in the top 3. Because it's so important, because it's going to tie a whole bunch of different things together. So what I did is I wrote these notes kind of in a medieval setting to help you kind of understand this. So you all suck at reading, so I'm going to read them to you in a somewhat jacked up Australian / Scottish / British accent. Okay? Now, you as an audience have one line to participate in. Okay? And you'll see that in
This
the
is how
line.
you teach. Involve the class.
Huh?
Participation.
Yeah, just,
know
you
force-
have one line. Okay, actually, there's 2 words.
Did you know net force divided by
Okay.
U?
Okay, all right, so here we go. Once upon a time in the kingdom of Physician, there were 2 opposing forces. One represented the forward-looking people who wanted progress and were very positive. The other was the faction that opposed everything that the positive people wanted and were generally considered to be negative. Thus, in the kingdom, there was always a struggle between the 2 forces. The positive people had a variety of tools they applied in their battle. They could push, shove, lift, hurl, heave, and once they discovered mechanized equipment, they started using rocket engines and hot air balloons. Theirs was viewed as a positive force since they were trying to move the kingdom forward. In opposition to such forward-thinking endeavors, there were the negative people who opposed everything the positive people would attempt, and they were negative. Eyes.
How did you know?
I just guessed, dude. I've got to be quick.
As with the positive people, they too had various tools at their disposal, but they were limited to only 2 tools, friction and gravity. Friction and gravity were generally referred to as the opposing forces and took away from the endeavors of the forces applied by the positive people. Negative forces could only be used in special circumstances. If positive people were trying to move something horizontally, then the negative people would use friction to oppose the applied force. The more friction there was, the less positive force remained. The positive people were trying to get something into the air, vertical motion, then the negative people would use the weight calculated by taking mass times your gravitational acceleration. As is true of every epic battle, protocol had to be established to determine who won or lost each battle. After much wailing and gnashing of teeth, it was determined that a mathematical system was to be established that the net force would equal your applied force plus your opposing force. Okay. All right. So let's chit-chat. So here's what we've got in a simple example. So here I've got a hydrogen-filled balloon. Okay? Not a big deal, other than the fact that it's all jacked up because somebody was messing with it. Okay. Now, so here's the balloon, right? And if I let go of it, whoop, up it goes, right? So, obviously, when I'm holding this thing, there's a certain amount of upward force acting on me. But, why don't I begin to slowly lift upwards?
Because you have more downward force caused by gravity.
Okay.
More gravity.
Now, this is like this problem on the assignment. If I'm sitting on a bathroom scale and I hold the balloon, there's going to be a slight, very slight decrease in the reading on the bathroom scale. Because by holding the balloon, I'm not affecting the downward force created by gravity. So the chair, in effect, has to provide a little bit less normal force because the balloon is kind of helping me out and lifting upward. So let's say I take a binder clip, I'll just go with this one, okay? And I hook this up and I let go of it and it begins to drop. So by hooking the binder clip up, what have I done to the upward force created by the balloon?
Nothing.
Absolutely nothing. I have not changed the upward buoyant force, right? But let's just think this through systematically. When I let go of it, right, which direction does it begin to accelerate? Downward, right? It begins to accelerate downward. So what's the direction of the imbalanced force?
Down.
Downward. So here's what you've got. If you look at this from a visual standpoint, here's the balloon, right? It has a certain applied force, okay? And the buoyant force works because the hydrogen gas inside of here is less dense than the air around it. So it's displacing a fluid. Air is like a fluid. We'll spend a lot more time talking about buoyancy force. But air is a fluid. And so right now, the air that it's displacing, right, is less than the hydrogen that's inside of it. Therefore, I get a buoyant force acting up. So I've got a certain applied force going up, but I've also got gravity pulling down on the binder clip. So which one's bigger? Gravity pulling down or the applied force acting up?
Gravity.
Gravity. So my net force then is going to point downward. Got that idea? Life's good. Now, if I put on a smaller one, okay, so take this one off and put on a smaller binder clip, okay. Now, when I let go of it, now what's happened?
Upward.
So,
Another small one on.
Yeah, can we see if it like
just
bounces?
chill out. Okay, we'll get there. Okay.
Chill, bro.
So now, when I let go of it, what's bigger? The upward force. So now I have the exact same applied force going up, right? But now my opposing force acting down is less. Okay, so there's my gravitational pull. So the difference between those two is creating a positive net force. Now, if you go what Giggles up here is all excited about, okay? If I put on a second binder clip,
Oh, don't do it.
Oh my god.
and let go of it,
That's crazy. Add like a paper clip.
oh,
to it.
just,
It's gonna even out.
Like
Okay.
paper.
It's gonna
We're gonna
hurt.
have to start adding paper.
okay, just chill out, okay? Now, when I let go of it,
Dude, it's
does it still accelerate?
Yes.
Yes, but now, what's happened to my gravitational pull?
It's increased.
It's
It's even.
gotten bigger. So now, basically, I'm real close, right? I'm very, 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 very close to making this thing bounce. So if I want it to just hover, what has to happen between the two forces?
Cancel out.
They basically have to cancel each other out. So if I put on a paper
How
clip,
did I guess?
okay,
You need a
So you have to have a
smaller,
small,
smaller paper clip.
or try a
Yes.
Or like a shred of tape, maybe?
yeah,
a shred of tape.
or like one of the binder clips and then the paper clip.
Whoa, hold on. So that's maybe,
It's so delicate.
What's that do? Oh, you're gonna rip it off. I was like,
Well,
if you expand.
you know, it's one of those deals, if you want a paper clip to break, it won't, but if you don't want it to, then it will.
So you just ruined a perfectly good.
I did, but it's in the name of science.
Too much, too much, too
half
much. We're gonna have to do tape.
You need even smaller.
Half
paper
off.
clip.
Tape,
Rip half of it.
Okay, now the other thing that's gonna happen is if I just let that sit there long enough,
The hydrogen.
The hydrogen-
Run out.
leak out. So let me try just one little piece of tape. So hold on.
What kind of tape? Yeah, that's masking.
Scotch.
No, Scotch too heavy.
That's scotch. That's scotch.
Masking's the like
This might
thick
not
one.
work.
Yeah.
Oh my god.
Guessed it, perfect.
Yeah.
Okay?
Dude, that's so weird.
Oh, it's coming to me. The friction.
Yeah, no, okay. So, now at this point,
Oh.
oh, you ruined it.
No, it's still good.
Okay.
I just
Let it just sit
created a
there.
draft.
No, like, can we see how long it? Well, I mean, you can talk.
Thanks. I appreciate that.
I think it needs a little off.
No, I think we're okay.
No, I think you should.
Because I'm also losing hydrogen, okay? So, let's just kind
All
of
the
let
more
that
reason.
sit
There we
for
go.
a little bit.
Why is it moving?
Because there's air moving in the room.
It's gonna tape.
Okay.
Get taped.
Are we good?
Oh, it's stuck.
All right.
I'll give it back.
Okay. Hunter, we get the idea.
I know, I'm giving
Hold
it to
on,
you.
no, we're good. We're good. Okay.
He's gonna get it.
Now, the other ultimate application of this concept is helicopters, which I happen to have. Okay?
Chopper?
Now,
In Mount
no.
Apache.
So this is the beauty of teaching physics, is that you can go buy toys and say, oh, I need it to teach my class.
Okay, is this where our taxes pay for?
No, I actually bought this myself. Okay.
Alright, you put it on them.
But, so, right now, are all the forces balanced out?
Yes.
You got gravity pulling down, and the table is providing the normal force.
You can look
Okay?
at it and just tell.
Now, if I just give it a little bit of power, okay? If I give it just a little bit, why doesn't it take off? It does have a hook at the bottom.
You can, like-
It's so cool.
Are you gonna pick up stuff?
No.
Put a paper
You know,
clip.
you know.
Okay, shh, okay. When I give it just a little bit of upward force, why doesn't it take off? What'd you say, Ellie?
Because gravity is more than that upward force.
Yes, I'm applying a certain upward force, but it's not enough to overcome the downward force of gravity. So if I go to full throttle, okay,
Drop the hook.
hold on. There.
Pick up the balloon.
That's no.
Ah, turn. Well, I was trying to drop the hook and fly it all at the same time.
I don't think it's
Okay.
This thing.
Somebody just died.
You ever play?
Okay.
Get your hand off. Doesn't have that paddle. You're lucky those aren't actually.
Okay. Now,
Pop the balloon. Pop the balloon.
no. When it just hovers, okay? When it just hovers, what do you know about the forces? They're balancing out. Now, if I wanted to accelerate upward,
Are you
I
getting
give
this,
it,
Maddie?
I mean,
Maddie, make sure. Go with it, Maddie.
okay? Now, if I wanted to go down, what do I do?
Decrease the upward force.
Yes. So when it's just completely balancing out,
I know.
okay?
Almost had the light.
How far can you drop the hook? Yeah, try it here. It's right here.
Get him a basket.
Oh, God. That was an epic failure. The hook won't stay down. Here, we'll give it a close-up.
It's tail spinning. Just go.
Wait, you landed.
You're good.
Am I good?
Yeah, you landed.
Go straight up.
Good job.
No.
Oh, we fly out of the canyon of death. Okay.
Maddie, you are not
Maddie,
three.
It's
right over.
Stuck the landing. Okay. All right. So, get that back. This is what I do after school. Are you grading papers? Yeah, as far as you know. Okay.
I like this job.
Okay. It's like, okay, what other teacher could go a helicopter and say, oh, I needed to teach? Okay, boom.
The
All right.
aviation.
Well, yeah, we don't offer aviation
Why do you
classes,
say that? Actually, we have a drone class
It's a
now.
club.
Okay.
Like a drone.
All right.
Okay. Do you know they have professional drone racing now in football stadiums?
Really?
Those things are flying at like 80 miles an hour and it's so scary.
You been to one?
Watch videos and it looks just
Wow,
terrifying.
that's impressive.
Look at that drawing. That was
It's
good.
right now.
Wow.
Pretty decent helicopter.
Wow.
Years of sitting through boring physics lectures. You got good at drawing helicopters. Okay. So, this is what's known as, it's a general classification called a elevator problem. It's a combination of helicopters and elevators, hence the term elevator problem. So, but they all play out the same way. So, let's say, to make this math easy, let's say that the mass of the helicopter is 1.02 kilograms. So no matter what's the downward force acting on the helicopter? Gravity, which is going to have a value of what?
Negative 9.8.
9.8.
9.8. God, I don't know. When I think I know something,
How do you calculate the gravitational
mass
force?
times the gravitational
Yes,
force.
if I take mass times 9.8 meters per second squared, what do I get?
9.996.
So let's just call it 10. Okay, that's why I picked 1
Different contingency.
I think I can.
10.9.
Okay, so here's the deal. So I got a downward force of negative 10 newtons. That's it. Boom. So no matter how fast the blades are spinning, this is what's acting downward. So if I want it to just hover, how much upward force do I have to apply?
10 newtons.
10 newtons. So if I'm at 10 newtons, I'm either hovering or I'm moving up or I'm moving down at constant velocity. Okay? So as long as my upward force is 10 newtons, I could be hovering, I could be moving up at a constant velocity, I could be moving down at a constant velocity, but I'm not accelerating. If I want to accelerate upward, what has to happen to my applied force?
It has to be more than 10.
Yeah, let's say that I go to full throttle and my upward force is 12 newtons. So here's what you can do and what you can't do. So if I say, I've got a helicopter with mass of 1.02 kilograms, and I apply an upward force of 12 newtons to it, what's the acceleration of the helicopter? Okay, if that's all the information that you have, here's what you cannot do. Okay, here's what you cannot do. You just can't take the 12 newtons and divide it by the 1.02 kilograms and go, oh, there's my acceleration. Okay? Every problem where you have vertical motion or if you have horizontal motion and there's friction, you have to go with this idea that force net equals FAP plus FOP. Okay? Every problem starts with this. The net equals FAP plus FOP. Your applied force is going to be something that's making it move. A buoyant force on a balloon, a rocket engine, helicopter blades. Okay? Something is going to be making it move. You pushing it. So your FAP has to be an external thing. Your FOP is going to depend upon the situation. If I'm going vertical, my opposing force is going to be gravity. If I'm going horizontally on a surface, my opposing force is going to be friction. Okay? So every problem start with this mindset. Finet equals FAP plus FOP. What's the only situation if you're moving vertically where you don't have to worry about FOP? There's one situation. If you were where? Basically in deep, 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 deep space. Okay? So if I tell you I don't want you to worry about gravity, I will tell you explicitly in the problem. The effects of gravity can be reasonably ignored. If I don't tell you that, you worry about gravity if you're moving vertically. Okay? So literally, unless I explicitly tell you not to worry about gravity, this opposing force of gravity is always going to be there if you have vertical motion. Okay? Remember that, remember that, remember that, remember that, remember that. Okay? So unless I tell you, literally, and this is how I will phrase it, the effects of gravity can be reasonably ignored, you take gravity into account. Okay? Now, there's two things that net force always equals. FAP plus FOP. It also equals mass times acceleration. So here's the deal. I got a 12 Newton force acting up. I've got a 10 Newton force acting down. So if you want to look at this graphically, you go, oh, there's my 12 Newtons. I got a downward force of negative 10 Newtons. What's the difference between a 12 Newton force acting up and a 10 Newton force acting down? Acting which way?
I think
Upward. So I got a 2 Newton force acting up. So that's my net force. Then I'm going to divide that by my mass to get the acceleration. Okay? So in this case, somebody take 2 and divide it by 1.02, you should get like maybe 1.99 or something like that.
1.96.
Yeah, 1.96 meters per second squared. Now, what if I reduce the power, instead of 12 newtons, I cut it to 8 newtons?
Well, we're crashing.
Well, not necessarily. At some point I need to land. At some point I need to have negative acceleration.
You can't land.
It's just
Okay.
negative.
Just
one
accelerate.
point
Yeah,
nine six.
so here, no. So if I've got an upward force of 8 newtons, right? I still have the same opposing force of 10 newtons. So the difference between those two is going to be negative 2 newtons. I'm going to take negative 2 newtons and divide it by the mass. I'm going to end up with the same acceleration, but now it's going to be negative. Okay?
I don't like dropping that fast out of the air though. It seems unsafe.
I don't care.
They have a parachute.
Yeah. Yeah, unfortunately, helicopters have a glide path of like a rock. So if you lose
They don't
power on
glide
an
at
airplane,
all.
you can continue to glide and land.
It has
Yeah,
wings.
if you lose power on a helicopter,
dropping.
that's why I said it has a
And
glide path.
don't
glide
jump
path
out because
of a
you're
rock.
getting hit by the blades, sir.
Okay.
Oh, I've never even thought about that. In a
That's why they
movie.
just shoot you out.
Yeah, that's
Eject
why in
those-
movies they conveniently
eject those-
spin.
Yeah, think about that. You jump out of a helicopter, you're hitting.
Yeah, okay.
Oh, that would.
Chop you up.
You're right.
Bad thing. You'll use that.
Final destination.
Dude, it is going to be fast too. That might feel like a nice massage.
So let's say that here's a rocket. Let me
You're
count
getting
it.
all them chopped off.
Oh, dude.
Boy, oh boy.
Sushi you.
Okay, back there. All right. So I want to look at two situations. Situation number one, I've got a mass of 2 kilograms. And I've got an upward force of 30 newtons. Okay? And I want to find the acceleration of the rocket. So here's what you're going to do wrong. And don't do this. And you go, oh, Mr. Burkham, you never do this. Lie. Here, literally, this is the problem. I'm going to give you this, and you're going to say, oh, force equals mass times acceleration. I'm going to take 30 newtons
No.
I did that on the Sunday.
No.
and divide that by
No.
2 kilograms.
No, I would
You
never.
will.
Okay, again, you lie.
Two
And
times
you
8
can go,
9.8. Find the normal first, and then
shut,
find the difference.
shoot, just let me finish.
Yeah, I've never.
So, you take 30 and divide it by 2, and you're going to go, the acceleration is 15 meters per second squared, easy peasy. Why does everybody make physics sound so difficult? It's simple division. And you can do that if I tell you what? If you're in deep space and you can affect, and you don't have to worry about the effects of gravity. So, if you take 2 times 9.8, you're going to get 19.6. So I've got a downward force of negative 19.6 newtons. So this is my FAP. Here's my FOP. The difference between those two is my FNET, my net force, right? So somebody take 30 and subtract 19.6, you should get 10.4. Is it 10.4?
Yes.
Okay. Then I'm going to divide that by 2 kilograms.
5.2.
And I'm going to get 5.2 meters per second squared. Now, interesting thing happens. All rocket engines are rated at a certain value, okay? I mean, you're going to fire them at full throttle, and that's what they can do, 30 newtons. So let's say that I take that same rocket engine, and I put it of 30 newtons, but then I put it in a rocket that only has a mass of 1 kilogram. Now, there's 2 things that are going to happen here. If I reduce the mass of the rocket, what's going to happen to my opposing force? It's going to become smaller. What's going to happen to my applied force? Nothing. It's going to be the same because it's the same rocket engine. So here's the deal. If it's a 1 kilogram, now my opposing force is going to be negative 9.8 newtons, which leaves me with a net force of what?
21.2. No, that's wrong.
How about 20.2?
20.2.
Okay. So now look what happened to my net force. My net force has become larger.
Twice as much almost.
But here's what's also important. Instead, not only do I have a larger net force, but what about the mass that I have to accelerate? I have less mass to accelerate. Therefore, I have less, rhymes with inertia. Therefore, I have less inertia. Therefore, it's easier to get this rocket to move. So if I divide that by 1 kilogram, I get 10.2 meters per second squared. So when I reduce the weight of that rocket, I have 2 things going for me. I end up with a smaller net force, okay? Excuse me, a larger net force with a smaller mass, and then I also have a smaller mass to accelerate, which also creates a bigger acceleration.
That's why we want missiles to fire fast and blow stuff up, right?
Yeah, in general terms. Yeah. Okay, got that. Life's good. Fantastic.
If you're dividing by 1, how are you getting?
Yeah, how you getting
10.2?
What?
Divide
22 by 1, that's...
divide by 1.
Oh, I'm sorry. That should be 20.2. My bad. 20.2.
That's what it sounds like.
Okay.
I did it 10 times.
Oh, good. I'm happy for you. Okay, good. Put that on your college resume. I can make a machine gun sound.
Beat that.
No. I'll beat Reese. How about that? Okay, so stop that. Stand up. Rest for a second. Okay, teacher time. Teacher time. Teacher time. Teacher time. This is about me now. Okay. We're good? Okay. All right. So let's say that I've got a box. Okay, and this is all the information that you have. I've got a box that's sitting at rest. I'm going to apply a 10 Newton force. It's got a mass of 0.5 kilograms. Okay? I want to know what's the acceleration of the box. That's all I want. Have I given you any information whatsoever about friction?
No.
You don't know what mu is, you don't know anything. Now, in this situation, is gravity going to act as an opposing force? No, is it there?
Yes.
Yes. But if I take 0.5 times 9.8, I get 4.9. So I've got a negative 4.9 Newton force going this way. I've got an upward force of 4.9 Newtons created by the surface. So these forces are here. But unlike if I'm trying to lift the box, gravity is an opposing force. But I'm just trying to push the box. So if you get a problem like this is as easy as it can possibly get. If all what you're given is the 10 newtons, and you're going, here's the mass to get the net force, and you always start with this, that force net equals FAP plus phi. Can you in any way, shape, or form determine the opposing force?
No.
No. I mean, you don't have to worry about gravity because we're shoving it horizontally. I've given you nothing about friction, so for lack of an information, you just have to assume that the opposing force is 0. So if my applied force is 10 newtons, that means my net force is going to be 10 newtons. I divide that by the mass of 0.5. 10 divided by 0.5 gets me 20 meters per second squared. Okay? Boom, there you go. Easy peasy. So if you're not given anything about horizontal friction, you just take that net force, you divide it by the mass, there's your acceleration. However, what if I told you this? Same box, still got a mass of 0.5 kilograms. I'm still going to apply a force of 10 newtons. But now I'm going to tell you that mu is 0.2. Now what's my acceleration? So now, what's the difference between the first problem and this problem? I've given you the coefficient of friction. Guess what? You need to use that number. Okay? So, you know that mu equals force friction over force normal. So again, you have to be able to find this normal force without thinking. Normal force on a flat surface is the same as what? Force of gravity. Force of gravity is found by taking 0.5 times 9.8 meters per second squared, which gives me 4.9. So I'm going to take mu times 4.9 newtons to get my force friction. So somebody take 0.2 times 4.9 newtons. What do you get? What'd you get? 0.98. So here's the setup. This is 0.98 newtons. So this is why it is so important that you make a quick sketch so you know what's going on. I got an applied force of 10 newtons.
Do we have to?
Let me put it this way. If you don't...
He's not going to grade it.
Please don't do this.
No. Okay? If you don't, that's fine. But if you come up and ask for help, I'm not going to help you until you do.
Okay.
And if you don't draw it and it's wrong, you will get no points. So, if you're willing to roll the dice, roll the dice. I've been doing them longer than you've been alive. Guess what I still do? Diagrams. So, which direction is this force of 0.98 newtons going to act? Opposite. So, if you want to think about it this way, this is like horizontal gravity. Okay? So, I'm trying to push it this way. I've got an opposing force of negative 0.98 newtons. Is friction ever going to work with me to make it go faster? No. Has anybody ever tried to drive their car, let's say that you've set your parking brake, and you've tried to drive with your parking brake still attached?
Yeah, my girlfriend pulls my parking brake all the time.
So what happens?
It's not going, and I'm like, what is going on?
No, you go slower. Most
Where
of
do you
the
go
time.
slower?
Yeah,
Why do you go slower?
That's what I'm saying.
Because
Like,
more friction on your.
Yes.
Bigger mu.
With the same applied force from the engine, you have a bigger opposing force, you have a smaller net force, you don't have as much acceleration. So when you don't release that parking brake, you're creating an opposing force that's working against you. Therefore, you can't accelerate as quickly. It's like trying to drive your car and drag an anchor with you. It's not going to work well. So it's the same idea. If you've ever seen like the guys that are training, you have like on Gatorade commercials or whatever, they'll run with a parachute behind them. What's the role of the parachute? To create an opposing force, so you have to create more applied force to run quickly. Okay, so it's the exact same idea. So when you see the commercials with the guys running and they're dragging a parachute, physicists just always go, great, nice opposing force. Never. Okay? Looks cool, but all you're doing is creating an opposing force. Run uphill, it's the same idea. Okay, but that's not near as cool. All right, so if I'm applying 10 newtons of force and I have a negative 0.98 newtons, how much force is left over?
0.02 newtons.
9.02 newtons?
No, point. Oh, that's a 0. Okay, yeah.
Yeah, 0.98 plus 10.
Yeah, 9.02.
9.02 newtons. So somebody take 9.02 newtons and divide that by a mass of 0.5, and you should get 18.04. Okay? Now, if I go back to this one, when there was no friction, my acceleration was 20 meters per second squared. Okay, that was my acceleration. Now when I have friction, what's happened to my acceleration? It's gone down. Okay? Now, if I gave you this problem, let's stick with this block, same coefficient of friction. If I wanted to push it at a constant velocity, how much force would it take? If I want to push the block at a constant velocity, how much force would I have to apply?
Oh, 0.98.
0.98. Because if I'm at a constant velocity, what's the value of my net force?
0.
0. So that means my FAP plus my FOP have to add up to
0.
So if my opposing force is negative 0.98 newtons, FAP has to be positive 0.98 newtons. It adds up to 0. I can still have movement, I'm just not accelerating. Okay? Now, think about this in terms of a grand idea. Here I've got, we'll go with Hank. Okay?
Oh, Hank the Tank.
Hank the Tank.
Drop it gracefully. Nope.
Why?
Why are you so mean to Hank?
Because I can.
You're gonna
Okay.
chip it someday.
Huh?
Like chip your table.
No, not yet.
Have you been doing that for 20 years?
No. Hank's a relative newcomer. And the odd thing is, I don't even know how Hank ended up in my room.
You
It's
just
just-
got him.
With the
Yeah,
thing on
seriously.
it.
I
How'd
have
you
no
get that
idea
thing
how
on
this
it?
bowling ball got in
It's
my
kind of
room.
like Wilson.
Did it say
I don't
Hank on
know
it
how.
before?
It does. It says Hank right there. I mean,
What if like Hank's real parents
I don't
show
care.
up for him?
okay. It's
It's
mine now.
It's a bowling ball.
All right, it's a bowling ball.
That's
Let's be
pretty
honest.
has-
Okay, now, here's the deal.
Dude, everybody knows parents, dude.
Let's say that Hank has a mass of 5 kilograms. Okay? Reasonable. So, right now, how can I figure out the gravitational pull on Hank if his mass is 5 kilograms? Multiply 5 times, negative 9.8. Trust me, you're going to get negative 49 newtons. Okay? So, right now, there's a gravitational pull of 49 newtons acting downward. Right? Here's Hank, sitting on the table. So what's the force provided by the table? 49 newtons. Okay? Now, if I want to throw Hank up in the air, okay?
You didn't drill very good. Just kidding.
It's more coarse strength.
You talk one more
If
time.
if I want to throw Hank up in the air, I've got a downward force of negative 49 newtons. what's the minimum amount of force that I have to apply to make Hank accelerate upward?
40.
Anything above 49 newtons, right? Because if it's exactly 49 newtons, Hank's just going to be right here. Okay, right now I'm exerting an upward force of 49
Hold
newtons.
on, so think about this. You said that you have to apply that or more, but he's accelerating once you leave your hand.
But there are going to be two different accelerations. Okay? So if I want him to accelerate upward, okay, I have to apply maybe 52 newtons of force. So if I apply 52 newtons of force upward, what's my net force?
3.
3 newtons, because I got 52 newton force acting up, I got a negative 49 newton force acting down. The difference between those two is 3 newtons. So then I divide that by the mass, there's the acceleration. But that's the acceleration when it's in my hand. Okay? Now, but as soon as it leaves my hand, what's the only force left acting on Hank?
Gravity.
Gravity. So, in any situation, you can use force net equaling FAP plus FOP. So when I'm throwing Hank up in the air, my applied force has to be greater than my opposing force. But as soon as I let go of Hank, what's the only force left acting on Hank? Gravity. There is no FAP. The only force I have left is FOP, which now becomes my
Net.
which becomes an acceleration of negative 9.8 meters per second squared. Okay?
I'm starting to say faster than
I'm happy for you. Okay. Got the idea. So, shut that down for a second. All right. So, let me get you started. Let me get you started. So, on number 1, you've got a 2.73 times 10 to the 4th kilogram semi-tractor trailer. It's traveling at 108 kilometers per hour. I'm going to stop it in a distance of 58.5 meters. So here's the deal. You're going to stop this truck. Force net equals FAP plus FOP. There's no applied force. We're not pushing it and stopping it at the same time. So the only opposing force that's going to stop this truck is going to be what? Friction. You know an initial velocity, you know a final velocity, you know an acceleration. Or you can, and know a distance. You can find the acceleration. Multiply that by the mass, boom, there's your frictional force. Then on number 2, you're going to find the coefficient of friction. If that coefficient of friction is above 1, you have done something wrong. Okay, so your answer to number 2 has to be less than 1. Now, on number 3, force of 64.4 newtons, pull a chair, constant velocity. What's the coefficient of friction? What are the 2 most important words in problem number 3? So you're going to make all of the forces add up to
0.
So your FAP is going to equal your okay. Now, let's talk about number 4. I got a force of 18 newtons is applied to 1.5 kilogram box at rest. What's the acceleration of the box? Number 4 is the easiest question on the entire assignment. Do not make it difficult. Why is number 4 so easy? What did I not give you? Friction. Net force equals your force applied. There's no opposing force. All you have to do is use F equals ma. That's all you have to do on number 4. Now, let's look at number 5. On number 5, I'm going to apply the exact same force to the exact same box. But now I've given you the coefficient of friction. So now what are you going to have to determine? You have to find the net force, but first you've got to find the frictional force by taking mu times force normal. So on number 5, there's a whole bunch of things that you need to do on number 5. You need to calculate the force friction as your opposing force. You're going to draw a free body diagram of the forces, and then you're going to draw them in a head-to-tail method. This is to scale. This is not a sketch. Okay? I want this drawn to scale, like maybe 1 centimeter equals a newton, or 1/2 centimeter equals a newton. I don't want tiny little vectors. Okay? So keep that in mind. You're going to draw 2 diagrams for this. Then you're going to find the net force, then you're going to calculate the acceleration. On number 8, you have a rocket launched upward. The upward force is 129 newtons. The rocket has a mass of 5 kilograms. And the other thing about rockets is that technically they lose mass as they're going up because they're burning fuel. But that's going to get complicated, so we're not going to worry about that. So we're just going to assume that the mass remains constant at 5 kilograms. So now on 8A I say sketch a free body diagram of the forces. This does not have to be to scale. This is just a sketch. I want everything labeled though. So you're going to draw a force diagram. You're also going to draw velocity and acceleration vectors. Okay? Just 2 or 3 of each. I don't have to see the whole motion, but you're just trying to convince me that, hey, I know what's going on. So then you're going to calculate the net force, the acceleration of the rocket, and we're going to fire the rocket for 12.6 seconds. Find the velocity at the end of 12.6 seconds. On the back side, yes, there is a back side. At the end of 12.6 seconds, I shut off the engines. If I shut off the engines, what's the only force left acting? Gravity. So you're going to draw another set of motion diagrams, another free body diagram, and then on the way up, and then you're going to draw them again once it starts to fall. Then I want the net force acting once I shut off the engines. Do not make F difficult. F is the second easiest question on the assignment. Do not make it difficult. When you get to H, you're going to draw a velocity time graph. If your velocity time graph doesn't fit in this space, like you get up to like 600 meters per second, don't go, oh, Burkamp screwed that up. He didn't make the graph big enough. No, something is wrong. Okay? Your time, and remember, this is a running clock, just like the acceleration test. This is a running clock. Okay? Other than that, and then you got some other questions to answer. So, there's some stuff you're going to have to do on another piece of paper. Keep that organized so I know what it is. I'm done.